These are all examples of the exercise 5C from the Pearson Active Learn book. So in this, we've got an arc AB of a circle, centre 0, radius r, and it says it obtains an angle theta, radians at O. So if we draw a diagram of that situation, then we've got something like this. So we've got part of a circle, a sector with a radius r. We've got the angle there that says it's subtending, which is theta, and we're calling this A, B, and there's O, and so we're saying that this length AB is L. So I'm just going to do the first part of A, B, and C. So what we're going to use is the formula that the arc length is, so the arc length L is equal to theta r, and this is when theta is measured in radians. So theta must be in radians if we're going to use this formula. So the first one, we've got the situation that we're looking for L. So this is A1. And we're going to use the formula that L is equal to theta r. So what we can do is we can just put these numbers in. Put in theta is 0.5 at 0.45 and r is equal to 6. So just multiply them two together and we should get 2.7 centimeters. So we'll continue this. So we're going to do B now. So for B, we're now looking for the radius. So again, we're going to start with this formula. We've got L is equal to theta r, and if we rearrange that to make r the subject, we can get that r is equal to L over theta. And in our case, we've got the first one, we've got L is equal to 10 and theta is equal to 0.6. So we're just going to put them into the formula. So we've got that L is equal to 10 over the 0.6. And what we get there is 16.67 centimeters. If we're looking at C, now we're looking for the angle, theta. And so I'm going to do C1. And in this case, we've got L is equal to 10 centimeters and R is equal to 7.5. We'll start with our formula again. L is equal to theta R. But we're going to rearrange that so that we've got theta as the subject. So we're going to end up with theta is equal to L over R. And then substituting those values. So we've got L is equal to 10. And we've got R is equal to 7.5. If we work out the value of that, then what we're going to get is 1.33 radians. Incidentally, where the formula comes from, so this theta over r, if we consider that the circumference of a circle is equal to 2 pi r, then we've got a fraction of that circle. So that would be a full circle there. And if we've got a fraction of that circle, then the fraction that we would have would be the angle that we've got for the sector. So there, let's draw that again with our angle there. We can see the fraction of a full circle would be this angle, theta, out of the full angle in a circle. And if we're measuring it in radians, then the full angle in a circle is 2 pi plus 360 degrees equals 2 pi. So if we multiply that by 2 pi r, then we can see that the 2 pi's actually cancel. And so it simplifies to being theta r. Obviously, if we was working in degrees, it wouldn't be theta over 2 pi, this fraction. It would actually be theta measured in degrees out of 360. So we wouldn't be able to cancel it like this. So this is why this formula only works for radians. So now looking at question 3 from the same exercise, 5C. And we're given that we've got another sector of a circle. So we've got an arc AB of a circle and centre O. So I'm just going to draw that. It's always good to draw a diagram when you're doing these. It just makes it much clearer. So there's the situation that we've got basically. So we've got A, B, centre O. We've got radius is 6. And we're told that this arc length is L centimetres. We're also told that we've got a chord AB and that's got length 6 centimetres. So we've got a chord going from there to there. And that's length 6 centimetres. So we've got to find the value of L and giving our answer in terms of pi. So we know that because this has got radius 6 centimetres and it's a circle, then this must also be 6. And we can see we've got an equilateral triangle. And so we know that in degrees, all these angles must actually be 60 degrees. Now, because we're working in pi, we want that in terms of pi. Really, we could do with finding this in terms of radians, this angle here. So we can convert it. We can either, it's easier if you can remember just what 60 degrees is, or we can take our 60 degrees and we can convert it into radians just by timesing by pi over 180. So timesing the 60 degrees by pi over 180, we can see that the 60 and the 180 will cancel, leaving with a 3 on the bottom. So that's equal to just pi over 3. So that's my angle, theta, in terms of, in radians. We can show that with a little c, so it's like a cut circle there. And so now we're just going to go to the formula that we've got for arc length, and we know that L is equal to theta r. So all we're going to do is now substitute in these values that we've got. We've got theta is pi by 3, and we've got that the radius is 6. So I'm just going to tidy that up, just cancel there. That makes it a 2, so it's equal to 2 pi. So this is now question 10 of exercise 5C. So we've got a bit more complicated situation. So what we've got to first of all do is write down in terms of R and big R and little r, the length of OC. So we don't really need to look at any of the degrees for this part. But if we look at our diagram, we know that R is the radius there. So the distance from the centre to T, so CT, is going to be R as well. So because we know O to T is going to be R, big R, so OT equals big R, and CT equals little r, then we can see that OC is the big one minus the small one. So it's R minus R. So now we're going to look at part B. So using triangle OCE, show that this equation or expression is true. So R sine theta equals R, and then in the brackets 1 plus sine theta. So we're looking at this triangle OCE, and one thing that we do know is that since this is OB is a tangent to this circle, we know that actually that must be a right angle there, the angle between a radius and a tangent. And we were also told that AOB is 2 theta. So that means the whole way across is 2 theta. So that must mean then that this is half of it because it's symmetrical, and that must be theta. So I'm just going to draw that triangle again, just so we can see a little bit more clearly what we've got. So there's O, there's C, there's E, and that's a right angle. So what we do know is that that is R, and we know that the distance from C to O is going to be what we found before, which is R minus C, R minus small r. And what we've got to find is this expression. So we know that if we look at theta and we consider that's theta there, we consider just basically SOHCAHTOA, we can see that sine of theta, so sine theta, which is what we've got in this expression, is the opposite, which is r, over the hypotenuse, which is r minus r. So if we multiply through by the r minus r, we're going to get r minus r times by sine theta equals r. I'm going to multiply that bracket out now, and I'm going to get r sine theta minus r sine theta, small r sine theta, equals r. Take the minus r sine theta over the other side, so it'll become positive. Factorise the right hand side. And there we go, we've done it. So that's part B done. So the final part then, we're given the value of sine theta. We're told that sine theta is equal to 3/4, and we're told that the perimeter of sector AOB, so that's the whole of the shape, is equal to 21. So we've got to find the value of r, so the radius of the circle that's in the middle there. So what we can do is we can just try and come up with an expression for the whole of the perimeter of that. So we can see the two straight sides, so the perimeter of this thing, the two straight sides are equal, r and r, so we've got 2r, and then the arc length there is going to be given by theta times big R, according to our formula. So the formula is theta r, and we know though that the actual angle here is 2 theta. So it's 2 theta and then times by the radius again. So I'm going to just factorise that. I'm going to say that that's equal to r, take that out as a factor, and then I'm going to keep the 2 and the 2 theta in here, because what I'm going to try and first of all do is find a value for big R, or an expression for big R. So we can say that's equal to 21, because we're given that in the question. We can say then that R is equal to 21 over 2 plus 2 theta. So we're going to use that again in a minute. Now we're going to use as well this thing that we found in part B. So I'm going to rearrange that. I'm also going to use the fact that we're given that sine theta equals 3/4 and put that into that formula. So if I do that, then what I've got is 0.75 the 3/4, and so replace the sine theta by that, r is equal to small r, and then the 1 plus the 3/4, which is sine theta, is 1.75. So if I rearrange that further, get r the subject, small r the subject, I've got that small r is equal to 0.75 over times by the big R over the 1.75. And if I use the theta there, we can say that theta is sine minus 1 of 0.75. So I can get a value for R from that, 0.75. I can get a value for R from that, making sure that I'm in radians. So if I do that, just shove the numbers into here, then what I will get is that big R is 5.6816. A few more decimal places after that. I'm going to replace that in our formula here. So that means that small r is equal to 0.75 times by the 5.6816, etc., over 1.75. And then what I will get is three significant figures. That comes out as being 2.43. And that's in centimetres. So that's it. We've done it.